So in the last couple of videos, we've been discussing the development of the Bohr model of the atom based on experimental evidence from line spectra. But there's one piece that we haven't fully incorporated yet, and that's why each of these orbitals would have a particular energy level associated with it. And to talk about that, we need to bring in another model of the atom, the de Broglie model of an orbital. And as you may recall from an earlier video in this series, de Broglie demonstrated that tiny particles could also have wave-like properties. Electrons also act as waves. We are able to diffract them, so they have a wave-like nature. And if we stop and think about that wave-like nature, it then makes more sense why there would be distinct allowed energy levels for each of the orbitals in the Bohr model of the atom. So let's think about how different wavelengths would play in to that orbital, so to speak. To do that, we first of all need to remind ourselves of how waves combine. So there is such a thing as a standing wave, and a standing wave happens when you've got a wave essentially either going round and round or back and forth, such that it is constantly positively reinforcing itself. Because when you add waves together, if you add them in phase, so if I have this wave here and I add this other wave here to it, those two red waves stacked on each other perfectly, we get what we call constructive interference, and we get a bigger wave that I don't really have space to draw on my slide, but you can see what I'm getting at here. That's constructive interference. That's what we get when we have a scenario with a standing wave. If we tried to add together waves that did not act in phase, if we tried to add this wave here with this opposite wave here, we would just get a big flat line. And if we tried to add together waves that were slightly offset but not quite, we get partial cancellation. So given that electrons behave as waves, the wavelengths for those electron waves, for the allowed energies, are the ones where we get a standing wave. And this is where you really have to deal with the fact that I can't draw. So if we have our nucleus in the middle, if we were to have an electron, just let me put a couple of ticks here to try and make this picture slightly more functional to help me draw. Those ticks aren't really there. They're just drawing aids for Susan. If we have our wave going around like this, like so, you can see that it's constantly reinforcing itself. And so the wavelength associated with this particular wave will be an allowed wavelength. So this is a allowed wavelength. And we know that the energy is inversely proportional to wavelength. And so this will dictate a particular allowed energy. Therefore, the energy is also allowed. If, on the other hand, I had a wave that was going around like this, having all sorts of cancellation happen, just pretend that's an even sine wave. This would correspond to a wavelength that is not allowed, because we do not get a standing wave. And therefore we have an energy that is not allowed. and we can introduce this idea that the wave nature of the electrons is what allows for those orbitals to have specific allowed energies. Now, I am massively, massively oversimplifying this. Please be aware of that. The electrons do not sit there going along nice, neat little paths along the outside of the atom, all smooth and two-dimensional and everything else. You'll see later in my fun pictures where the electrons are moving all over the place, and the actual waves involved are probability wave functions. But this is the general concept. The key point here, that any given orbital is an electron essentially in a standing wave. And so this brings us to the end of our look at the Bohr model of the atom, which of course has to be combined with that de Broglie concept of the electron as wave. We are successfully able to calculate the energies of every state of the hydrogen atom. We can calculate the average radius of a hydrogen in every single possible state. We have experimental evidence that says these values are right. We have line spectra showing us the gaps between the energies, and we can do other measurements to measure the size, the radius. But there are some problems. This is not the final conclusive model of the atom. Electrons don't actually just go around the nucleus in a circle at a nice even distance. This cute little circle here, no, that's not what happens. And we still have some issues with angular momentum, but we kind of glossed over that because the math is beyond the scope of this course. And the calculations are really kind of limited. We can do them on hydrogen and other stuff with one electron. If we want to go beyond that, we need much more complex formulas, and we need a computer to do the math for us. And that, of course, as we saw earlier, is due to the fact that we would have to address not only electron to nucleus attraction, but electron-electron repulsion is a problem because the electrons are constantly moving, and so the distance between them is constantly changing, and so therefore the force of repulsion between them is constantly changing, because when they get close together they repel more, and when they get far apart they repel less. And it's just one big whole complicated thing to calculate. And so after this, we're going to be looking at more holistic pictures of the models of the atom, and we're going to be drawing pictures rather than doing calculations.